Let's have a short tutorial on resonance. And we begin with a review of the formulas for a series RLC resonant circuit. The resonant frequency omega naught is 1 over root LC. The half-power frequencies can be computed by those two formulas in terms of R, L, and C, or the one I prefer as a function of the resonant frequency omega naught and of Q. Q, the quality factor Q. The resonant frequency is the geometric mean of the two half-power frequencies omega 1 and omega 2. The bandwidth, the difference between those two frequencies, which happen to be L over R for a series RLC circuit only. The quality factor was defined this way: 2 pi, the peak energy stored in either the inductor or the capacitor divided by the losses in one period. Or even better, how much bigger the resonant frequencies than the bandwidth, or how much bigger the reactance of the inductor and the resonant frequency is than the resistance, or what is the same, how much bigger the reactance of the capacitor at omega naught is than R. When Q, the quality factor, is greater or equal than 0, in that case we can approximate omega 1 and omega 2 as being omega naught minus half the bandwidth and omega naught plus half the bandwidth. Let's have an example taken from the excellent textbook Alexander and Sadiku Fundamentals of Electric Circuit, a McGraw-Hill book. That example is presented there without solution. A series connected circuit, this one, has a value R of 4 ohms and inductance of 25 millihenries. Calculate what is the value of C, this C, that will produce a quality factor filter of 50. Well, we can do that. And after that, please find what are the half-power frequencies, omega 1, omega 2, and the bandwidth, of course. And last, part C, determine the average power dissipated at the resonant frequency, and also at the half-power frequencies, omega 1 and omega 2. Take then the peak value of the source. This source is 100 volts. Let's begin. We know that the quality factor is given by this general formula, but in our case, I prefer this one. The quality factor tells us how much bigger the resonant frequency is than the bandwidth. But there, we don't have omega naught, we don't have the bandwidth. Let's look for another formula, this one. The quality factor tells us how much bigger the reactance of the inductor is at the resonant frequency than the resistance. We know Q, it is 50. We know L and we know R. We can find omega naught? Absolutely. Omega naught from that formula is 8,000 radians per second, 8 kiloradians per second. But that quality factor is also how much bigger the reactance of the capacitor at omega naught is than the resistor. And now we know who is omega naught. And now we know R2. So let's find C. The capacitance is 625 nanofarads. We also know that that quality factor, 50, is how much bigger at resonant frequency, 8 kiloradians per second, is than the bandwidth. So we can compute the bandwidth now. 8 kiloradians divided by 50, that is 160 radians per second. That is the bandwidth. And because the quality factor is greater than 10, we can approximate the half-power frequencies as being omega naught minus half the bandwidth, that is 8,000 minus half 160, that is 7,920 radians per second. And omega 2, the high one, is the resonant frequency, 8,000 radians per second, plus half the bandwidth, that is 80 radians per second. By the way, 8080 was the very first 8-bit CPU of Intel that I programmed as a teenager. Anyway, at resonance, omega naught, all the voltage appears on the resistor, you know that, because the inductor and the capacitor, they cancel out, and the source sees only the 4 ohm resistor. It is applying a sinusoidal voltage to that resistor with a peak value of 100 volts. We compute that power as V squared over R. What V? The RMS value of V. This one. The square value of the RMS divided by R. And the RMS value is the peak value 100 divided by root 2. Square it, divide by 4. 1,250 watts. That is the average power dissipated by the circuit and the resonant frequency. But we want to know what is the power dissipated by the circuit and the half power frequencies. And the name itself is giving away that power. That power is going to be half this power. 1250 divided by 2, 625 watts. Before proceeding, let's have a comparison of the basic formulas of a series RLC circuit and a parallel RLC circuit. The resonant frequency omega naught is computed the same way, 1 over root LC. The quality factor, well, the quality factor for the series one is how much bigger the reactance is than the resistance. Whose reactance? Either the first one, omega naught L over R, that is the reactance of the inductor, and the other is how much bigger the reactance of the capacitor is than their resistor. And what about for the parallel RLC? Well, the quality factor is how much bigger the conductance of the resistor is than the susceptance of the inductor or the susceptance of the capacitor. What? Well, you remember that the inverse of impedance, Z, is Y, the admittance, right? You remember that the inverse of R, the resistance, is G, the conductance, correct? Right. Well, the inverse of a reactance X is the susceptance B. The susceptance of a capacitor is J omega C, and the susceptance of an inductor is negative 1 over omega L. Well, the quality factor for the parallel RLC circuit is how much bigger the conductance of the resistor is than the susceptance of either the inductor or the capacitor. And the bandwidth? Well, the bandwidth is the same. It's how much bigger the resonant frequency is than the quality factor. That's what it tells you, the bandwidth. The half power frequencies are given by that wonderful pair of formulas, one addition and one subtraction, to give us omega 1 and omega 2. That is proportional to the resonant frequency omega, and the factor depends on the quality factor. But for high quality filters, when Q is greater than or equal to 10, omega 1 and omega 2 can be computed in an easier manner. Omega naught, the resonant frequency, minus half the bandwidth or plus half the bandwidth. Let's go into an example of a parallel resonant circuit, also taking from the Alexander and Sadiko proposed there without solution. A parallel resonant circuit has a resistance of 100 kilo ohms, an inductance of 20 millihenries, and a capacitance of 5 nanofarads. Calculate omega naught, omega 1 and omega 2, and also the quality factor and the bandwidth of that parallel resonant circuit. What is omega naught? You say piece of cake. That is 1 over root LC. That is 100 kiloradians per second. That is out of the way. Now, Q, the quality factor for a parallel one, tells us how much bigger the inverse of the resistance is than the inverse of the impedance of the inductor. This one, that is 50. Check this out. With such a large quality factor, you know that if we find out first what is the bandwidth, finding omega 1 and omega 2 is only one addition or one subtraction away. So let's do that. That's Q. What is the bandwidth? Do you remember another definition for Q? Yes. Q was how much bigger the resonant frequency is than the bandwidth. We know Q, we know omega naught. We find the bandwidth 2000 radians per second. And then omega 1 is going to be 1000 radians per second below, and the other 1000 above the resonant frequency. Because Q is greater than 10, we can approximate omega 1 as being 1000 below 100K, that is 99 kiloradians per second, and omega 2 is 1000 radians per second above the resonant frequency, 101 kiloradians per second. And that is that. Now, let's consider an exercise that is also proposed in the Alexander and Sadiko, but solved differently there. This circuit presents an inductor and a capacitor along with a resistor, but the capacitor and the inductor are neither in series nor in parallel. That makes it a more general circuit. It is fed by this cosine-powered source. 10 millihenries, half a millifarad, 20 ohms. Calculate the resonant frequency of the circuit in hertz. I think that I didn't compute that in hertz, but in radians per second. So please, the final answer in the video, divide by what? Divide that by 2 pi and you get the hertz. But I leave that up to you. Let's solve the circuit in radians per second. We're going to compute the impedance seen by the source and then find the frequency at which the angle of the impedance is 0. That is, a frequency at which the whole impedance is just a resistance. That is the impedance seen by the source. You see, this is the impedance of the inductor J omega L in series with a parallel of 20 ohms and this capacitive impedance J omega C. Let's replace omega by omega naught that we're trying to find. Let's take the angle of that is the argument of that, equate that to 0, and that is the equation we need to solve for omega naught. We solve it, and we get that the resonant frequency is 435.9 radians per second. And you're saying, wait a second, wait. I'm with you that you can find the impedance seen by the source, and that's it. I am still with you when you say substitute omega by omega naught that we're trying to solve for. We're still with you when you're trying to make that a real number by guaranteeing that the angle of all of that Z is 0 here. Argument of that impedance at omega naught is 0. But then you go ahead and you say that you solved that and you got this value. How exactly? Did you use any fancy computer software to do that? Not really, but I used the fancy HP50G calculator to do that. I enter that impedance, that is J, and multiply J by omega. I use X instead of omega, it's easier to type, and multiply that by the inductance. And then I add the parallel of the resistance of 20 ohms and the capacitor's impedance at the frequency X as well. That is going to be the impedance that I'm trying to write as the function of X, which is omega. And all of that, I want to take the argument of that complex number and equate that to 0. That is the equation we're trying to solve. But before solving that, let me plot it. I use a plot setup of the HP50G. I enter there, I paste what I've cut from the equation writer, and I say, I want to plot that. Let me go to the Windows dialog and say, plot that between the frequency zeros and let's say 500 radians per second in the vertical axis, automatic scaling. Erase the previous plot, draw that. That is the angle of the impedance as a function of omega, which is X. You see that it's 0 at omega 0, of course, and it's also 0, that angle, at a frequency that is over here. That is the zero crossing we're looking for. That frequency of the zero crossing is our omega naught. How do we find that? Well, the calculator allows me to trace the cursor. That is to put the cursor on top of the curve, click, and then this XY shows me the coordinates of that. And when I move the cursor with the right arrow, it tells me what are the coordinates of that. 434 radians per second and the value of the angle there is negative 0.02 radians. It's pretty close to a 0. Let's use that as an approximation. Now we go out of there and into the numerical solver of the calculator in red on top of the key 7. Solve an equation. Which equation? The same one. It's the one that we plotted. Give an approximate value for the solution 400 and click, hey, solve that equation. There, the solution is 435.89 radians per second, which is the value I showed you before. Let me plot that angle of that impedance as a function of omega over here in the plot at the bottom. The angle of that impedance here is changing with frequency. But at this particular frequency, whatever that is, that phase is 0. Well, it shouldn't be called phase, but that is the way that is labeled on that axis. The angle of the impedance is 0. Whatever frequency we have here, that is the frequency of resonance of that circuit. Observe one thing here in the magnitude diagram. At that specific frequency, the magnitude of the impedance reaches a minimum value, as we had anticipated. Well, you say, wait. At that frequency, the resonance frequency, this one, the magnitude in decibels of the impedance is 0 decibels. But 0 decibels implies that the impedance has a value magnitude of 1 ohms, right? 20 log of 1 ohm, that is 0 decibels. So, at the resonant frequency, the whole circuit looks like a 1 ohm resistor. Yeah, that's right, 1 ohm. At that frequency, the whole circuit looks like a 1 ohm resistor. And you say, how can that be? The resistor we have in that circuit is a 20 ohm resistor. Oh well, look at it. At that frequency, 435.89 radians per second, at that one frequency, we can convert the parallel of the resistor and the capacitor into an equivalent resistor in series with an equivalent capacitor. At the frequency of resonance, we evaluate the impedance of that circuit. First, this is the impedance of the inductor J omega L, J 436 ohms. The admittance of the parallel circuit at the bottom is 1/20 plus the inverse of the impedance of the capacitor at that frequency. If we invert that admittance, what we get is the equivalent series impedance of that pair of elements at the bottom. Do that with a calculator, and what you get for impedance of the circuit at the bottom is 1 ohm in series with one equivalent capacitor. And the impedance of that equivalent capacitor is negative J 436 ohms. Draw them all together in series, and of course the inductor's impedance cancels out the capacitor's impedance, and you're left with only 1 ohm resistor as we anticipated. 1 ohm, 20 log of 1 ohm, that is 0 decibels. At zero crossing, which happens at 46.89 radians per second, we have minimum impedance, and the impedance value is just 0 decibels, 1 ohm. That confirms what we've said before. And that is all. That is the end. Thank you very much for watching, and I hope to meet you again in our next video.